Right, grade 11s. So this is our second lesson in the finance unit. Here we're looking at compound interest. The first part of this lesson, we're going to be figuring out a future value of money, like making an investment now and figuring out what it's going to be worth down the road. And in the second video, we're going to turn it around and still use compound or like exponential growth, but figure out how much we need to invest today in order to end up with a goal in the future. So maybe you're trying to make $1,000 to buy something. How much do you need to start with is what we'll figure out in the second video. So our goal is to solve problems that involve calculating the amount of an investment for a variety of compounding periods. That sounds wordy. The compounding periods, we haven't used that phrase before, so we'll define that. In this note, have a little bit of practice from the textbook, and then this afternoon we're going to be having a quiz / assignment. I'm not settled on what format it's going to take, but an evaluation in the afternoon. Okay, so what is compound interest? I already showed that in the first video, the fact that it was an exponential growth, but the basic principle of compound interest is that you are earning additional interest on interest you've already earned. So once you earn your first interest payment, it's added to the principal, and it's going to start collecting its own interest. So the idea here, you start with some amount of money. In year one, this is earning 9% per year, which is crazy, but 9%. So you've maybe put in $1 and now you're going to get 90 cents back. Sorry, you've put in $10 or 10 there. You put in $10 and you're going to end up with 90 cents of interest. Now your bank balance starting in year two is $10.90. And that next year of 9% interest, you're going to earn more money, so 98 cents. And that carries on and carries on. So the stack gets taller and taller more quickly as time passes, because the interest you've earned is also going to be earning interest. Here's a little cartoon. If you want to pause and read it, I welcome you to. The idea is that it's like an interest question, so calculating an amount of money. So do pause it, have a quick read, and then we are going to answer that question. Okay, so the question there is, how do they arrive at the solution in the cartoon? How do they end up with $1,219 using $1,000 principal and 2% interest? So I'm just going to uncover what that answer is, the solution. And this is an exponential growth, so it has a format similar to our lesson yesterday, where the multiplier in the front is your starting amount of money, the initial amount. In the brackets for the base of the power, we have 1 plus an interest rate raised to an exponent that tells you how many times you've grown. I've worked that through using BEDMAS, and the final answer is 1,000, sorry, that's sloppy there, 1,218.99, and in the cartoon they've rounded that off to the nearest dollar. So approximately $1,219. Okay, so this is an exponential growth problem, which we have already seen, and this is going to be the style that we look at this morning. So exponential growth, talking really only about money, not all those other things like bacteria growth and population growth. We're doing all finance for this last few days. Okay, so this goes along with your handout. You have the fill in the blanks on yours. So compound interest and calculating future values. The future amount of money will be the sum of the principal invested, so your starting money, and its compounding interest. Compounding means it's like growing interest, right? We get more each year than we earned the previous year. We can use this formula, which looks like the same kind of structure as we used yesterday with exponential growth, but with the variables changed a little bit. So I put here a little note to recall. This is the formula we were using yesterday for exponential growth. P naught was the initial value. R was the rate written in decimal form. N was the number of growth periods. And P at N was the final amount. So this has the same structure, but some new letters. I'm going to advance my slide here. I have it written out, typed out. A is the future amount of money, or future value, some people call that. FV. P stands for principal, or present value. Sometimes people say PV for present value. In the bracket where we used to have an R, we're using lowercase I for interest rate per compounding period, and I'll explain more what that is on the next slide. And N, the exponent, is the number of compounding, or we can say growth, periods. And where the thing that's growing is your money or your bank balance. All right, so you can pause and copy the rest of that down. So the definitions there talked about compounding periods. So here's a breakdown of what those are. I have here a chart that has the number of compounding periods in a year and changes that we're going to have to make to the interest rate and the time in the formula. So the idea here is that formula is meant for annual interest, just like with simple interest. Remember in the first video, I equals PRT, and this had to be in years because the rate was in years. So it's like kind of designed for annual input information. So this is annual. This is what the equation's meant for. So we're going to take the given interest rate and just kind of use it if we're talking about annual compounding, meaning like once a year, we're going to do this interest calculation and add interest to our bank account. The time, we can just use it exactly as it is. If we're compounding semi-annually, that means we're going to actually collect interest twice in a given year. So maybe we get interest added to our account at the end of June and the end of December. So every half year. That means we're going to take the annual interest rate. We're going to take the annual interest rate R and we'll divide it by 2. So if for example, if the interest rate was 10% per year, we're going to take 5% of it in the first half of the year, 5% of it in the second half of the year. So break it into 2 chunks. So we'll take the interest rate, split it in half, and we're going to have twice as many time periods. So for example, if we are putting our money in the bank for 1 year, we're going to get interest twice. If we're putting our money in the bank for 2 years, a time of 2 years, we're going to get interest deposits 4 times. Okay, so we're going to double the number of years and cut our interest rate in half for semi-annual. So this chart continues with a couple of other scenarios that are very common. Quarterly compounding means 4 times per year. So that 1 year we would actually have 4 interest collections or compounding periods. And we could take our interest rate and split it into 4 equal chunks, or divide it by 4 to find the I value in the equation. Alrighty, monthly means we're collecting interest 12 times in a year. So we'll split the interest rate into 12 chunks and collect interest 12 times as often. Weekly, that number is 52 because there's 52 weeks in a year. Bi-weekly is what lots of part-time jobs pay. And like retail jobs, you get a paycheck every other week. So if there's 52 weeks in a year and you get paid every other week, you're going to be getting 26 paychecks. So if you are collecting interest bi-weekly, the number's the same, 26 times per year. 26 times per year And we can break our interest into lots of 26 equal amounts. And then the last one there is daily. So this is like a lot of calculating if it happened in the real world. But the idea here is that instead of getting your 10% interest at the end of the year as one big lump, you would take it and collect 1/365th of it on January 1st. So a tiny little fraction of the interest rate you would collect on day one of the year. And then on day two, you would collect another tiny little bit of your interest. So it's broken into teeny chunks, but that means that the interest is being added sooner. So that's actually helpful for making your money grow fast. All right, so you can copy the rest of that chart down. Making sure the most important part is that you're making connections between the words and how many chunks per year that refers to. All right, so that's going to be important in the questions that we do. Okay, so this is not on your handout, but it refers back to that cartoon. So I'm just going to flip back there for a second. So this one, they were starting with $1,000, collecting 2% interest, compound interest, and ending up with $1,219. Okay, so this is kind of a follow-up question. How would that, where did it go? How would that amount of money change if we were compounding semi-annually? Okay, so we were assuming in that first one that we got all of our interest once at the end of the year. What if we split it into two chunks? So what I mean there is that the interest rate is really 2% divided into two chunks. So we're getting 1% in each half of the year. Written as a decimal, that's 0.01. And that's the number that I've filled into the bracket. The other part of that, this number didn't come out nicely, but I can fix it. The money was invested there in that scenario for 10 years. The exponent here becomes 20 because our number of compounding periods is actually the time multiplied by 2. So 10 times 2, which is 20, and that's the number that goes in the exponent. So we end up earning a little bit more than the 1,219. So that's what we earned with annual compounding. And this is what we're earning with semi-annual compounding, meaning we get our money a little bit sooner, like halfway through the year, and that's going to earn its own interest. If we change that to compounding quarterly, the number of time, or the number of compounding periods will be the 10 years times 4 quarters in a year. So we're going to get interest 40 different times. And then the inside of that bracket has to do with the interest rate, which was 2% divided into 4 equal chunks. So that's 0.5% or 0.005 as a decimal, and that gets added to 1 in the equation. And we earn a little bit more money, so an extra 70 cents by collecting it more often. And then the last one is daily compounding. For this one, the number of compounding periods is 10 years and 365 days per year. So we're going to collect interest so many times every day for 10 years. So that's my exponent. And the base, I didn't even change this into a decimal form because it would be a tiny little decimal, but I took the 2%, divided it into 365 equal chunks, and I've just put that in decimal form instead of percent. And that's what I used in the bracket. And we earn like an extra $1 or so. Okay, so the idea here is that the more compounding periods there are in a year, the more money you're going to end up earning in interest because you're having it deposited sooner and added to your principal sooner. All right, so back to your actual note. Oh, one more little idea here. How does changing the compound period affect the amount of the investment? You earn money faster when there are more compounding periods per year. Okay, so that's exactly what I was just saying on the last slide. All right. Example 1. $1,000 was invested at 2.8%. This notation here means per annum. Per annum or per year. So it's like the annual interest rate, but you're going to compound it quarterly. What will the investment be worth in 4 years? So the principal is 1,000. The interest rate was 2.8%. I've changed that to a decimal. I'm dividing it by 4 because we're compounding 4 times per year. That means in each quarter of the year, we're only really collecting 0.7% interest. The exponent, the number of compounding periods, is going to be 4 years multiplied by 4 quarters per year. So we're going to get interest 16 different times. So I'm going to substitute those numbers into this formula, 1,000, and then in brackets 1 plus 0.007. I'm just going to give the answer to that. And the exponent is 16. Following BEDMAS, the exponent part of this is what you will solve first. So 1.007 to the exponent 16, and then multiply by 1,000. And the final answer for this is 1,118 and 8 cents. Okay, so it will have grown by $118.08. Example 2. How much interest is accumulated over 6 years for a loan of $2,000 that is charged an annual interest rate of 15.6% compounded weekly? So this is kind of like the opposite situation. We have a loan this time, so we're borrowing $2,000, and 6 years from now when we pay it back, we're going to owe more than that because of the interest. All right, so the principal or the starting amount is 2,000. The interest rate was 15.6%. I've changed that to a decimal. This one says compounded weekly, so I'm dividing by 52, dividing the interest rate into 52 separate chunks. Do I have that? I don't have that as a decimal yet. Let's see. 0.156 divided by 52. 0.003. And we're talking about 6 years that we're borrowing the money for, and we're being charged interest every week for those 6 years. So 6 times 52 is 312. So that's just stuff given in the question, and now I'm going to look and make sure we know what we're solving for. How much interest is accumulated? So I is what we're solving for. That's not actually part of our equation. Okay, so if you remember the compound interest formula from an earlier slide, capital I is not part of that equation. We will be able to figure it out, but we're going to have to do this equation first and then figure out the amount of interest. Okay, so I'm going to fill in what we do know. The final amount wasn't told to us. The principal is 2,000. 1 plus the interest rate becomes 1.003. So it's just a number slightly bigger than 1 as the base. But we're going to multiply it by itself many, many times. 312 times. The answer from my calculator says $5,092.38. so if we borrow $2,000 today at this really high interest rate, we're going to end up owing $5,000 6 years from now. This is not a good deal. All right, so if this was a loan that you took out, you should be trying as hard as you can to pay it back sooner than 6 years, because that is a lot of a big increase. The increase is actually what we're trying to find here. In an earlier question, we said that final amount is made up of principal and interest, and this time we're solving for the interest. So the final amount was $5,092.38. The principal was $2,000. We can find that interest amount by subtracting $2,000 from both sides. We're doing a takeaway P. So that comes out to be $3,092.38 worth of interest. That's like extra money above and beyond your original loan that has to be paid back. Yikes. Not a good deal. Okay, so that's it for problems in this part of the lesson. These are ones where we're given a principal or starting amount. So we know the principal and we're trying to find the final amount with the help of that equation. There's some practice in your textbook that goes with this video, and there'll be a second video posted that does kind of the reverse problem, where we know the final amount and we'll figure out the principal.